Okay guys, this is an overview explanation of your Model K11 AC/DC power supply kit from Elanco, and I'm going to go through some basics. You've seen the schematic and that's been explained to you. Now looking at the prototype circuit before we actually assemble it and put it together, I have a couple test points in here. We're going to do a quick analysis to piggyback on some of the lab activities that we've done earlier. So what I have here is the yellow voltage meter is hooked to the output, the DC output, and set to measure DC output. My red multimeter is hooked across our diodes, and so we are looking at the DC, the pulsating DC equivalent coming off the diodes. So both diodes are producing a little over 24 volts. If you recall back, we calculated our, the rating on this is a 120 to 13 center tap transformer, and we found that here at the school we were getting measurements that were just a slight bit higher than that on the output, and this is at 120 to 13, that should give us about a 18 volt. And we were seeing something a little bit higher than that. So here we go. As we look at this and do our little analysis here, watch the output, and we're going to rotate. We shouldn't see any change on the diodes. As we rotate our output, we're slowly increasing from 0 to a maximum DC output. Should be just over 15. So I'm going to slowly crank the potentiometer up, and we see that 15.6 is the unloaded output voltage that we're getting on this. Now I've moved my red voltage meter to analyze the voltage between the emitter and collector of Q2. That was our power transistor. It's the one with the heat sink on it right there. And the emitter to collector voltage differential here. So here we are, we're at our 15.6 maximum, 15.59 maximum output on our DC power supply, and we're seeing 8.2 volts. I'll notice that as we decrease our output voltage on our potentiometer, that the collector to emitted voltage goes up, and that's because that portion of the voltage regulator is splitting the voltage potential from the output to the collector emitter. And so you see, as we go down to 0 on our DC output, the 24 volts that we saw at the diode rectifiers has been recycled back through our transistor circuit, and our collector emitter voltage shows all of that potential there, and we are getting 0 at the output, essentially from the emitter to the ground. We see 0 volts. So collector, that power transistor plays a key role in our voltage regulator, as we use that to control the current across our Zener, current draw across our Zener diode. So now we're going to do a quick switch on the Zener diode. Okay, so here we are, and we're looking at our Zener voltage. Notice 16.8 on the red multimeter, and we are just about at, I thought I had her at maximum output, just about at maximum output. DC output 15.5 was our maximum unloaded output on the yellow multimeter. Notice that as I decrease that output, there is no change on the Zener voltage. The Zener voltage stays a fixed 16.8 all the way throughout the circuit. As we scroll down, the potentiometer is going down, and we bring it to 0 on our output there. We're still fixed 16.8. So our Zener diode, that's this component right here, in its reverse bias state, is allowing us to control, regulate the reference voltage to the base of Q1. And that reference voltage is split across this potentiometer right here. And the potentiometer is what allows us to vary our output voltage, but the Zener regulator is a key front end piece to this overall voltage regulator in this circuit here. So we see a constant 16.8. It is a 17 volt Zener diode, and that is hooked in reverse bias here, so it plays a very key role. One final check, we're going to look at what is going on here at Q1. Q1 is being used as a switching transistor for this, and so let's move our probes and take. This is our final evaluation, and in this evaluation we are looking the yellow voltmeter still hooked to our DC output. Our red voltmeter is now hooked to the emitter and base, and we are measuring the potential between the emitter and base of Q1. That is our small NPN transistor at the beginning of the variable voltage regulator. Watch as I very slowly crank my potentiometer and rotate that. Watch the red output. So you see we're at 0.3. Let's get this to be a little more precise. We're at a 0.30. And currently, there's nothing on the DC output. We're still reading 0. But suddenly it hits 0.4, and we start to see an output effect. Basically, we have activated, we've begun the saturation of that transistor, and it's become a switch. Notice when it is fully saturated, we're going to be probably about a 4 volt output, and we reach the 0.54 mark there. It will not go above 0.54. It's going to stay there in its full saturation state. Basically, that is its fully on state for that Q1 transistor, and that is activating the current flow to Q2. Q2 is helping us regulate the current draw from our Zener diode. So regardless of what the output is, the emitter to base on Q1 is going to be a steady 0.5 volts as it has been activated or turned on, and so that transistor is set to its switch state. So hopefully this gives you a little better insight about the performance of the power supply, and hopefully you are now prepped to do your quiz.